So last time we talked about the canonical analysis for general relativity. So what we have finished last time is basically those canonical variables for GR, for general relativity. So firstly, you have position variable. Position variables. Those position variables are, for example, the three metric Q. So people use Qij, the components. So here we always use components. So including Qij, Ni, and so N is a shift vector. N is the lapse function. Ni is a shift vector. N is a lapse function, and Qij is a 3D spatial metric. And correspondingly, you also have momentum variable. Okay. So by the way, so here there are more property to call it generalized position variable and generalized momentum variable. Well, because you have learned canonical classical mechanics, so you know what this generalized means. So it doesn't really mean the position and momentum of the particle because we are dealing with a field theory. So these are just called position variable and or generalized position variable and generalized momentum variable for the field theory. They have very little relation with the usual sense of position and momentum. Okay, so those momentum variables are so-called conjugate to those position variables. So they are one-to-one correspondence between momentum and position. So we have momentum variable Pij, okay, and we also have Pn, I, and Pn. Okay, so they are so Pij is conjugate to Qij, and the Pi is conjugate to Ni, Pn conjugate to S. Okay, and how to get them is just the functional derivative of your action with respect to the Q dot, with respect to the time derivative of the position variable. So this is just the standard definition, and this is delta Ni, and this is delta S dot N dot. So this is the definition. Okay, so this is the position variable and momentum variable. So as we discussed last time, so once you compute this Pni and Pn, so immediately you got two constraints. Yeah, so you got so here you got constraints, so more so-called primary constraints. Which is Pni equals to 0 and Pn equals to 0. So this is just the speciality of the Einstein-Hilbert action, that the action, once you do 3+1 decomposition, it's completely independent of Ni dot and Ni. All right. So this is our result last time. So once you have this position variable and momentum variable, you can construct so-called phase space, or more precisely, you can construct a set of coordinates in the phase space. Okay, so let's consider how to say so let's call this like our phase space, and this is our phase space. Phase space. So, well, I mean, what is a phase space? Phase space is also a manifold, right? But now it is a infinite dimensional manifold because you have infinite number of degree of freedoms. So these are Qij. They are fields. They depend on space and time. So they are fields. So for every space-time point, you have a Qij. So which means you have because you have infinite number of space-time points, so you have infinite number of Qijs, and that's why you have infinite number of degree of freedom. So therefore our phase space is really infinite dimensional. So let's call this phase space. Let's give this notation. Let's call this maybe script M. Oh no, usually we call it P. Yeah, usually call script P. Yeah, and so to be phase space is not just a manifold, but it also has some additional structure, just like well, for our space-time, it is a manifold plus a metric, right? And we call that the space-time. But phase space, it is a manifold, what we call P, and also you have additional structure called Poisson bracket. Yeah, so this is, you can view this is the definition of the phase space. Phase space is just a manifold plus some additional structure called Poisson bracket. Yeah, so I will write down the definition for the Poisson bracket separately. Okay, and in your classical mechanics, you have learned you have used the phase space definitely because you learned classical mechanics, but that was always a finite dimensional phase space because in classical mechanics you're always dealing with a finite number of degree of freedom. Okay, so now once we have those position variable and momentum variable, we can construct the phase space, and we have a coordinate system in our phase space. Okay, so the coordinate system are just given by those variables. So these variables are actually coordinates in the phase space because they are related to numbers, right? So these are Qij, for example, Ni, N, and you have P, Ij, and Pn. Okay, so these are coordinate system on the phase space, and being coordinate system, they are functions. They are firstly functions on the phase space because how to view them? They are functions. So for example, the metric. So give you example, the metric Qij x and t. You see, and suppose you fix this x and t as a number, as I said before, and this x and t, they are just the generalized labels, right? And just like ij, they are indices. But I mean, these x and t, they are just you can also view them as indices, but they are just continuous. They are just the continuous indices, right? You view x and t, they are also indices like I and j. You fix ij, the number of I and j, and xt. For example, well, I'll give you more explicitly. Suppose you say q11 and 0, 0. Okay, so this is very specific. So at I equals 1, j equals 1, and x equals 0, t equals 0, and then this is definitely a number, right? This is a number. But you can also view that this is a function, right? This is a function because this maps a point in the phase space to this number and to this number q. Yeah. So this is also a function. Function of phase space. Because this is like you pinpoint a point in the phase space, and you tell the value of q1100 at this point, right? So maybe this is here, some point here. Yeah. And once you pinpoint this, you point to this point, and you say the evaluation of q1100 at this point, it gives this number. So more precisely, this quantity, it is a function. So for every point, you have a value of this, and that's why you have a function on the phase space. Similarly, for all the other variables, so Qij, Nin, and Pn, and so on. And they are functions on the phase space, and more they are special functions because they form a basis. They form a coordinate in your phase space. Okay. All right, so this is you construct this phase space, and you also need something called a Poisson bracket. So Poisson bracket, it is a bilinear map of functions on the phase space. So this Poisson bracket, it is maps functions. It is a bilinear of two functions, two functions, two function, let's say f1, f and f prime, to Poisson bracket of f and f prime, yeah, and which is also a function. This is again a function. So so here it is always a phase-based function. Phase-based function. So for any two functions on the phase space, you can compute the Poisson bracket, and the result of the Poisson bracket is also a phase-based function. Yeah. To be specific, well, of course, it satisfies several properties like anti-symmetric, like Jacobi identity, and so on. And this is some properties you have learned in your classical mechanics. And Poisson bracket is generally satisfy these conditions. But so let me write down in general the Poisson bracket in terms of those canonical coordinates. So they are called conjugate variable. They are also called canonical variables. They are sometimes also called canonical coordinates. Okay, so let me write down for any two functions. Well, these two functions can be written as qij, p pseudo ij, and other canonical variables. Similarly for f prime. They are functions on the phase space, so they are functional. They are somehow functional. In the usual sense, in the usual terminology, they are functionals because they are functions on infinite dimensional space. Okay. Anyway, so let me write down the Poisson bracket. So this is the definition of this Poisson bracket is given by the following. So you have an integral over d3x over the spatial slice sigma, and you have functional derivative. You have to perform functional derivative with respect to all the canonical variables. Q is qij x and dot f prime delta p will x minus. So you have to taking derivative with all the conjugate pairs. For every pair, so here Q and P, they are conjugate pairs. So you have this kind of anti-symmetric product. Okay, so but this is just the first term. You also have another two terms. So let me like this. And plus, you have other degree of freedoms because you have also n and pn. And so delta prime pn. Probably I have to put Twiddle on top of that. Okay, and you also have another conjugate pair. Okay, so this is the definition of this Poisson bracket. You can compare with, well, if you So if you compare with Poisson bracket in finite dimensional system, so you can see that the Poisson bracket, well, let me change another color, maybe compare with the Poisson bracket you have learned before, equals, let me consider just, well, let me consider finite dimensional system. I labels degree of freedom, then this is given by partial f, partial qi, partial qi, partial f prime, partial pi minus partial f, partial okay, so this is the Poisson bracket you have learned before, right? So here you have, in the finite dimensional system, you sum over all the degree of freedom I. So here you have indices qi and pi, right? You have qi as your position variable, you have pi as your momentum variables, and you basically derivative respect to the conjugate pairs, right? Conjugate pairs, and then you sum over all the degree of freedom. And this is manifestly anti-symmetric with respect to f and f prime. And so here you see you're just doing similar things. The only difference is that here you get some continuous indices x. You have space index x, and so which means that you have to somehow sum over x, okay? And so this sum over x now is become d3x. So this is not a discrete sum because x is a continuous variable, but you have to replace the sum by integral. Yeah, so this is how we define this Poisson bracket. Okay, so because they are field variables, so you can't use the partial derivative because they are infinite dimensional quantities.
I have a question. We're doing the integral over some volume in a three-dimensional because the x is actually a three-dimensional variable, right? If the function is a function of some four-dimensional, say x and t, then the integral, shouldn't the integral be like over some four-dimensional?
No, so this is in the spatial slice. All the quantity are defined in spatial slice. This is maybe also properly called the equal time Poisson bracket. So it means that so say well, again, finite dimensional allowed. Okay, so so we are in blue color. Okay, and so the f it is function of p and t and q of t, right? And f prime it is the same p of t but at the same t, q at t. Okay, and p I q I p I q I. Okay, and then remember how you compute the Poisson bracket in classical mechanics. You don't have sum over t, right? And you know all the quantity are time dependent, but you don't really compute integral over t, right? And this is the result is given by this, and you know everything is dependent on t. So this means that you are actually computing the equal time Poisson bracket. This is so I mean, but by Poisson bracket, we always means that they are equal time. Equal time Poisson bracket. Okay, so but being Poisson bracket, it is always equal time. So this is just about phase space. So phase space, you can view that it is. Yeah, so you don't really take into account the time evolution, but at some point you take into account time evolution, but time evolution will generate a curve in the phase space. Yeah, so this is, well, I don't know how so this, let's call this curve gamma of t. So this is the time evolution. So every point will be variables at the same time, but time flows and these variable change and you generate a curve, and that's the time evolution. All right.
Yeah. So, okay. Thank you.
All right. So now, but here you have some special structure in this phase space because you have two constraints. Okay, you have two constraints. So it means that you have to it's not all the phase space are useful, yeah, in our situation, because we have to all the physics are constrained by these two primary constraints. It means that we have to, what we're actually interested in is so-called a constraint surface. Constraint surface, yeah. So where this P I n equals to P n equals to 0. Okay. So well, I mean here this constraint surface is very simple because Pi and Pni and Pn, they are just coordinates. So which means the constraint surface is just the surface where those, you just remove those coordinates. Yeah? You just set those coordinates equals to 0. So this constraint surface is very simple. All right. So now the next. So once we have the phase space, so what we know next is the so-called canonical equation of motion, which is Hamilton's equation. Okay, so before Hamilton's equation, so you can derive from this Poisson bracket the Poisson bracket from canonical variables. Yeah? So for example, you can easily compute this Poisson bracket. So for example, Qij x and t and p kl. Sorry. Another thing I forgot to add is this Poisson bracket is written in case of kappa equals 0, so gravitational constant equals to kappa equals 1. Yeah. So here, suppose we put back kappa, you just put a kappa in front. Okay. So how to get it? So let me first come into this Poisson bracket, and I tell you how to get the kappa back. Okay, and x prime t. So if you compute the Poisson bracket, you just compute the functional derivatives. And last time I showed you how to compute functional derivatives, you just get a bunch of. So when you compute functional derivative with respect to canonical variables, because they are canonical variable already, so what you get is just a bunch of delta functions, and you are integrating by this integral over delta functions. Okay, the result is really just very simple. There's a kappa. If I put the kappa back, pi delta lj, and there is a symmetric between I and j, and then there is a delta 3. Why? So there's a symmetric between I and j is because qij and pij, they are all symmetric tensors. Yeah, they are symmetric quantities. And here you get a delta 3 ij is because they are canonical variables. So you can, again, you can make finite dimensional analog between qi t and pi t. What you get is just the delta I pj, delta ij, right? Delta ij. And here these I and j, our analog of this I and j is here ij and x. Yeah, x, they are also indices. So here this delta ij, including both delta ki, delta ki, delta lj, and also including this analog of this delta 3 x and y, because this is a continuous version of delta. Yeah. So this Poisson bracket indicates that, and they are really conjugate. They are really conjugate variables. So sometimes when we talk about canonical analysis, when we say, okay, and some one variable and another variable, they are conjugate variable, we simply write down their Poisson bracket. Yeah. So this Poisson bracket here, it already indicates that they are conjugate variable. Just like in classical mechanics, right? P conjugate PQ Poisson bracket equals to delta. It means that they are conjugate variables. And it also indicates that our Poisson bracket has to be written in this form, because this is a standard form of conjugate variables. Because, and also again, in finite dimensional mechanics, you know, once you know this Poisson bracket, you immediately know the Poisson bracket between arbitrary functions are written in this form. Okay, it's the same thing. Okay, let's come back to how to get this kappa. So before, when we derive, remember when we derive this P and Q, we set in this derivation here, we set kappa equals to 1. Okay? And remember this, the action is supposed to be 1 over kappa integral minus GR d3x. Okay, so when we write this formula, we set kappa equals 1 to simplify this calculation. Okay, but then suppose we take the kappa back, so which means that this Pij is not anymore because S has 1 over kappa, so this Pij will have 1 over kappa in front. So Pij, okay, so this Pij will have some one. Let's say Pij twiddle primed equals to 1 over kappa of this, and so then for this primed Pij, you will have P primed and Q and P twiddle prime, you will have equals to delta with no kappa. But this P prime equals to 1 over kappa P. So then you move this kappa here. You remove the prime. That's why you have a kappa in front of delta. All right. So that's why you have a kappa here, and in the same manner you have a kappa here. So this is technical details about how to get a kappa back, and also there is some convention issue. Is that sometimes we use this action, sometimes we will put a minus sign in front. They are just two different physically equivalent conventions to calculations. So in this formula, of course, I didn't put a minus in front. This is, we work like this. But at some point, I think when we talk about extra variables, and probably next lecture, we will use the other convention. So better I talk about it here. So suppose we use action which has a minus sign, then here you have a minus sign, here you have a minus sign, which means here you also have a minus sign, and here you also have a minus sign. So it can happen. So it will happen next time. So we will, for some convenience, we will just shift the convention next time. But here, just to let you know, it is just very easy to show the relation of two different conventions.
Dr. Han?
Yeah.
If for the chart of the polynomial, I mean the total one be include out, right?
The dot?
Delta,
Sorry, let's say again.
be include out, I mean.
Can you repeat your question?
I mean for the result of the polynomial, the delta function should be included out.
Well, you mean, okay, so if you do this calculation, you have, for example, Q, you put a Q and P here. Well, here you definitely got 0 because they are independent variables. So here you have a Q, here you have P, and here you have Q, you have P. This term goes away because delta Q delta P equals to 0. But here you got, for this derivative you will get one delta function, and for this derivative you get another delta function, and then you integrate the x.
Okay.
So you glue two delta functions and into a single one.
Okay.
All right. Okay. So well, it's a good exercise. Should I take it as a homework? Maybe it's good to work it out for you. It's really easy, but very elementary homework. Check this. Okay. So now let's so these are this completes our phase-based analysis. Let's come to next page. Okay, so now let's talk about the equation of motion. So Hamilton's equation. What is Hamilton's equation? Hamilton's equation. This is very simple. So for any phase-based function, so for any phase-based function f, well, here you can write as a function of qij xt pij xt and so on, other variables. Okay, and the time evolution, let's say this is f dot. F dot means the time derivative equals to the Poisson bracket of this f and the Hamiltonian. Okay? So this is Hamilton's equation. Okay? And the Poisson bracket is the one we defined above. And this Hamilton here is the following. I have introduced the Hamilton, the Hamiltonian. So this H is the Hamiltonian. H is given by integral over space and C plus Ni Ci. Okay, and here I better write. This is very useful. So I write implicitly what is C and Ci. C equals to 1 over kappa Q and Pij minus 1 half P square minus square root determine Q with 3 curvature and Ci equals to minus 2 over kappa pi p total I. Okay. Well, this Hamiltonian equals to that plus some boundary terms. Boundary terms. We have all the calculation we have ignored boundary terms. So at some point we'll get them back, but at the moment we have to ignore those boundary terms. Okay. So this is the Hamiltonian. In principle, when you derive the Hamilton's equation, you plug it in and compute Poisson bracket. But so you can also easily write down the Hamilton's equation for canonical variables. Well, for example, this Q dot ij will be time functional derivative with respect to delta p ij, and then p twiddle dot ij equals to minus functional derivative of h with respect to q and ij. Yeah. So this is again an analog. So similarly for n dot, yeah, you can n p n dot and also ni dot p n dot. You can easily work out the relation with functional derivatives, and this is a analog of in ordinary mechanics that Q dot is partial h partial p and P dot is minus partial h partial q, right? And these equations everybody should be familiar with. This is just classical mechanics. So here you can see this is just a generalization of finite dimensional system. So here you have additional labels. So here is just a simple generalization from finite dimensional finite dimensional classical mechanics to infinite dimensional field theory. Yeah, and also those equation of motion you can also derive from variational principle from okay, I have the Lagrangian here. Remember, Lagrangian equals the action equals to now it's 1 over kappa integral d t d3x. Well, all those PDQs. Okay, Q dot ij and plus n and plus the others. Well, actually, you don't have n dot and ni dot, so you don't have the others. Plus et, I think this is minus